Hello everyone, welcome to NSeries Icon webinar. My name is Rachel. With us today we have John Min, Director of North America Field Application Engineering, who will introduce how NSeries vector processors deliver high computing efficiency and flexibilities to help you achieve optimal design of AI applications. Before I hand the mic over, I have a few housekeeping items to cover. First, today's webinar will be available on demand on Andy's website and YouTube channel. The slides will also be available for download on the website. If you have any questions for John, please leave your questions in the chat box. We'll answer your questions after the presentation. So without any further ado, I'd like to welcome our speaker today. John, over to you.
Okay. Good day, good morning. It's a wonderful morning in California. Thank you for joining us on RISC-V online webinar. Today we'll talk about how some of our processors, specifically including our packed SIMD DSP processor and vector processor, can be used to obtain high computing efficiency and flexibility. And we'll go over the AI applications and some use cases. Okay, let's dive right in. So the agenda today will be the diversity of AI use cases. Then we'll talk about the processors that fit into different usage cases for those. And then we'll talk about our new neural network SDK targeted for AI, and we'll summarize. So those of you who who's not familiar with Andes, we are a pure play CPU IP company. We are 15 years old. We have over 200 licenses worldwide. And so far, we have over 5 billion SoCs shipped with our technology. We are a major open source contributor. We maintain many open source projects. And we also have our own proprietary toolset as well at GUI. We are a founding member, premier member of RISC-V Foundation. We run many of the task groups. Our CTO is a vice chair of a technical steering committee. We're on the board of directors, and we're RISC-V ambassador. We are a RISC-V company. So we are listed in Taiwan Stock Exchange, and we have offices around the world. I work in the Silicon Valley, USA office. All right, let's jump right in to talk about the AI use cases. Typical use case people really associated with some of the AI is image and vision processing. So image classification, object detection, segmentation, spoof detection, and the phones, face unlocking, eye tracking, and some of these visual processing. But the secondary AI use cases are voice and speech, audio front-end processing, keyword spotting to wake things up, voice command, speech to text, and text to speech, obviously. And then what's coming up interesting is natural language processing. We're seeing some of these, and also real-time translation devices. And then lastly, it's any signal. The AI can be used any signal to detect pattern and take action, like sensors with force, pressure, accelerometer, vibration, temperature, radar, LiDAR used in ADAS, specific pattern recognition, perhaps predictive maintenance, and lastly, and most importantly, perhaps healthcare. So how does Andes processors fit into all these AI spectrums? We divide our processor into 3 broad categories. At the bottom, the green, we have the NSeries processor, something called baseline. We call it baseline. So these are the standard 32-bit or 64-bit processor that mostly used in a command path or someplace where signal process or the math operations demands aren't very heavy. As we move up to more applications like face trigger, object detection, intelligent HMI, barging beamforming, those start needing more math computations. Then we have D series, which are DSP or packed SIMD, or P extension, RISC-V P extension embedded, and A-series, which supports virtual memory space to run Linux if desired. Again, moving up the performance spectrum, we have V-series processor, which are CPUs enabled with the V extension, or vector extensions. These could include face unlock, face recognition, bokeh image processing, avatar gesture recognition, and more higher resolution cameras, and including ADAS, where you might have multiple cameras or multiple sensor inputs that needs to be processed in real time. On the high end, data center applications, which may require multi-cluster solutions as well. So we have different processors for different application spaces. Let's talk about those in a little more detail. The NSeries processors are our baseline processors. This is a fundamental building block of a processor. These come in 32-bit or 64-bit flavors. They can come in multi-processor. So it'd be the designer's choice to design a single fast CPU, maybe multiple slower CPU as well. There are choices. And these include some Andes-specific V5 extensions. Some of the major features of these processors, they probably include floating point unit, caches and local memory to access data and instruction, ECC for security and reliability. And we have processors starting with 2 stages, 5 stages, 8-stage pipeline. And they run typically frequencies up to about 1.2 gigahertz and TSMC 28 nanometer worst case. Moving up in performance, we have the D-series and A-series processors. These are enabled with our DSP or PAC-SIMD instructions, which are defined in a draft P extension, the RISC-V specification. Will be built on top of our baseline N-series processor, and we include DSP SIMD instructions. So, and A-series specifically has a memory management unit for virtual memory or to run Linux. The SIMD width follows the XLAN or processor width. The 32-bit SIMD is available with 32-bit processors. 64-bit SIMD is available with the 64-bit processors. And typical data types are the int8, 16, and 32-bit integer types. And these are very efficient for data computation, very compact, and reduced instruction count. Lastly, we have the vector series processor. Now this is as we're adding on to base and also SIMD DNA series. And now we introduced RISC-V vector extensions. These are configurable, and the configurable is key to fit in many different spaces. So VLAN is 128 bits, 256 bits, 512 bits, depending on the application. We support length multiplier for increased precisions. And now we support much more data types. We support int 4-bit, 8-bit, 16-bit, 32-bit, 64-bit integers, 16-bit, 32-bit, 64-bit floating point, plus a couple of integer data types that are AI specific, like int4 or in bfloat16 as well. So these are very flexible processors that you could dial in the performance that meets your application. So what does this look like for data computation? So with the RISC-V baseline, with the RISC-V instruction set, along with our specific Andes V5 extensions, custom extensions, we could increase the performance about 20% over standard RISC-V instruction set. At the same time, reducing code size by about 10%. When we add the DSP or SIMD P extension, we could now start accelerating the math-specific functions. Over the baseline processor on the left, we could speed up the image classification cipher10 by about 14 times. So basically, the CPU could run 14 times slower and will provide same performance. Keyword spotting algorithms can increase that the DSP can increase performance by about 9 times. So certainly it depends. Adding more hardware accelerates performance, and usually because there are so many less cycles being executed, it actually improves power as well. So lastly, vector extension. Vector extension is we follow the latest standard. Currently, it's still not a final standard yet, but it is available. These define V extension defines over 300 instructions. They're very scalable vector registers, very fast. Are taking more performance. Oops. Sorry, are you guys all back? I lost the internet for a second. So as we move up the performance, the CPU takes more responsibility for the performance. So we add the P extension, which adds that DSP math capabilities, and then we move from purely control to some of the signal processing, and perhaps these are good for always-on low-power applications like keyword spotting, or very low performance, cost-sensitive applications. Moving up, we could implement vector processor. These are for, nice thing is the vector processor now adds significant performance capability to the processor. Perhaps the applications like AR, VR, surveillance, real-time image processing is possible. And ultimately, you could have a cloud or data center application where you might have many heterogeneous processors, some control, some signal processing, some vector enabled in a multi-cluster configuration for AI data center applications. So those are the standard, some of the standard extensions. We have something called ACE in this custom extension. These allow for custom acceleration of both the instructions. You could create custom instructions or perhaps custom data paths. So for compute function, for the fundamental kernels, convolution or gem, you could create few key instructions to accelerate kernels. If you do DSP signal processing, this might be a butterfly operation. Idea is perhaps at the same time accelerating a specific function that benefits lower power as well. As we move up to the control plane, the ACE could be used as a specific high bandwidth control and data movement path for the accelerator. So you have baseline controller. We could use ACE as a private accelerator controller as well. So you can in fact create private buses, not load the main bus. Lastly, when we're using the vector accelerator has a very high throughput, but it also places high demand on data movement. So one way to solve this would be put in a large local memory. When that's not possible, or you're in a bigger data set, especially with data center applications, we can create a custom streaming interface using custom extensions. We call it the ACE custom ports. to do both the control and the data movement. So let's take an example, human-machine interface applications, where we start with the baseline plus perhaps a SIMD DSP processor. It could handle some of the simple applications like color cancellation, noise reduction, some math functions like FFT, do some coefficient calculations and filter back. And then with the always-on modules, we could do voice triggering or keyword spotting with always-on. And perhaps we could wake up an external engine that actually does speech and text recognition. And those can be implemented with the baseline and RISC-V vectors. So simple processor would wake up a vector-enabled processor to do heavy-duty lifting of the audio and signal processing, as in keyword, automatic speech recognition, speech synthesis. Moving on, and this could lead connect to the data center, where a data center could handle natural language processing and more higher level functions. So the AI human-machine interface applications have many levels, and each processor, certainly one processor can handle a very high processor, but you want to keep that running all the time. So there's smaller controllers that could handle keyword spotting. So let's look at the market, deep learning chipset global market. The market is set to grow about 40 to 50% combined annual growth rate for the next 5 years. It has been true for the last 5 years. Largest growth comes from ASICs, and these ASICs contain CPUs, DSPs, vector processors, and hardware engines. So this is a market that our processors are targeted. Those are hardware. Now, how do we really use those hardware? So we're trying to enable that the software usage and decrease time to market. So in this SDK, neural network SDK works with the standard framework from the hardwares to standard AI applications and signal processing, AI framework and kernels. Along working with our partners, we're developing and this neural network SDK based on LLVM compiler and very optimized DSP library. To that, we're adding a very optimized NN library, utilizing both the baseline, DSP instructions, and also vector instructions. So our DSP library is optimized for low-level DSP functions. These are basic building blocks of signal processing and runs on both the baseline processor and the DSP-enabled processor. They boost signal performance. There are over 200 functions. And we make it Simsys DSP library like APIs to make the porting code easier. And as you could see, over many different functions, average speed up of all the functions about 2.5 times the RISC DSP over baseline. And some functions can be accelerated 10 to 11 times. So it is a very highly efficient instruction set, DSP instruction set, plus a library. So on top of the DSP library, now we're going to add our specific Andes neural network library and TensorFlow Lite for micros. Our NN library is optimized low-level functions designed for both the RISC-V baseline, DSP, and RISC-V vector processors. And we want to boost this neural network performance by using SIMD and vector instructions. You'll have API that's compatible with Simsys NN. Again, shortening the time to market. If the NN library doesn't quite fit the applications, we could actually fall back to TensorFlow Lite for microcontroller. So the TensorFlow Lite and the NN library are very complementary. So some of the audio processing speedups, our DSP SIMD enabled processors have acceleration from about 2 to 4x on audio and music, MP3 decode, keyword spotting, and face detection algorithms. We could have about 8 to 9 times the performance. And then Cipher-10 image classification, we could get almost up to 15 times the performance, 15x performance. On the specifically on the Cipher-10 image classification speed up over baseline processor and our competition, we could certainly give 3 to 4x performance depending on different processors. 32-bit processor tends to be closer to 2 times. 64-bit processor tends to be close to 4 times acceleration. Okay, so we could increase this performance boost using our neural network and DSP libraries because we could run 3, 4, 5, even 15 times faster. That gives you opportunity to run the processor slower. And many factors. Slower processor is easier time enclosure, generally smaller. You run at less clock frequency. And overall, it leads to lower power and higher power efficiency. So that was DSP acceleration. Now the vector processor speed up, depending on the algorithm, SGEM, we actually see about almost 60 times acceleration. Some of the filtering functions, 20 to 40 times. And now the neural network CNN functions, we could get almost 20 times acceleration on the average. Same thing goes for 32-bit floating point basic math as well. So the library and the hardware is very optimized for high performance. That helps with the power efficiency. So let's look at an application, keyword spotting solution. Typically, there's voice trigger is designed there to always wake up the system. We want to consume lower power than ASR for always on usage. And key requirement is reduce false alarms. It's very annoying when you're talking and your phone, as Siri, goes off. So with voice commands, we want to design more hands-free solutions and simple and offline or edge processing HMI, human machine interface. So taking this application, using our software DSP and neural network library, accelerated by the hardware that's built into the processor. Looking at multiple algorithms, DSCNN, DNN, GRU, we get better than 85% to 95% accuracy with the varying instruction and data storage limits. And as collecting some of the algorithms, DSCNN takes about 3.5 million cycles. DNN is very low overhead, so about 180,000 cycles. And GRU algorithm, GRU model, takes about 5 million cycles for training and quantization tools. So it is very efficient in terms of performance, and it's a high performance, so it could reduce times. Okay, so what are we doing overall for AI? We're working with many partners in the DSP vision audio space. The tools, definitely, we're working a lot of time on tools for AI tools and IP. We have development tool partners who gives us simulators, hardware monitoring, and the development tools. And then on top of that, we're working very heavily with the open source community in terms of operating systems, middleware, and the compilers, low-level compilers as well. So AI applications are very well supported. It's moving. And so in summary, the RISC-V vector processors, our RISC-V processors support a variety of AI use cases from compact baseline for control, SIMD DSP for data signal processing computations, and then vector unit for even higher performance, efficiency, and configurability. Our neural network library, SDK, targets to boost the SoC AI performance, really to achieve good hardware utilization. and most importantly, improve time to market. There are 2 libraries available, and you could use either or both libraries depending on your application. DSP Library is targeted at signal processing, and then library is targeted for neural network operators. Lastly, ecosystem is advancing very fast to help you with AI development projects. So thank you for joining me. This concludes the formal presentation. If you have any questions, I'll answer any questions now.
Thank you, John. So if you have any questions for our speaker, please leave your questions in the chat box. I'll give you a couple of minutes to enter the question. Okay, we've got a couple of questions. The first one is, we knew AI technologies are evolving. We can see new AI models and new NM operators every day. So how does Andy support and adopt these new AI applications?
Well, so it's a great question. How does evolving models and operators, how do we support that? Well, we'll divide this into 2 different perspectives. First, from hardware perspective, feasibility and programmability of RISC-V DSP and vector extensions, it's much better than hardwire engine. Hardwire engine is fixed function, cannot be programmed. By using the using the DSP and vector extensions, we could support future AI technologies and achieve great performance efficiency. On the software side, we created our NN SDK library specifically as looking at the very low-level functions, which are building blocks of larger algorithms. So rather than focusing on supporting specific NN operators, we support the building blocks so they can be adapted quickly to new operators. And the ecosystem, we're continuing to work with the ecosystem, and we're planning an open source community using our DSP and an API so that any new operators can be quickly adapted using these fundamental building blocks to build those operators, support those operators.
Okay, we've got one more question from the audience. Is ACE open source, and is it architecture dependent? In general, how do you think is scope of RISC-V based AI machine learning processors as it is increasing in the past 3 years after looking at ICS 20?
Yeah, so ACE is a proprietary interface for us. A lot of CPU vendors support adding simple custom instructions, and we've gone much past that. We could add instructions, custom memory interfaces, custom control ports. It is available on most of our almost every one of our processors as an add-on. What was the second part of the question, Rachel?
It said, how do you think the scope of RISC-V based AI and ML processors as it is increasing in the past 3 years after looking at ICS 20?
Yeah, so for the past 3 years, the RISC-V community and RISC-V International have spent a lot of time developing the vector extensions, especially looking at machine learning applications. We as an Andes as an early customer in this space, data center application space. So we learned a lot by working with our lead customers. The RISC-V vector specification is maturing. Hopefully within this year, it'll become finalized, which would even, today, the market's growing. A lot of people are working on vector extensions from both hardware and software side. As they become more final, and as more products, chips, vector-enabled chips come out on the market, we do expect, as I said, as we looked at the slide, almost explosive growth in using RISC-V vector and DSP extensions for AI applications.
Our next question is, what are the die sizes on various nodes of technology?
What a downside of various technologies?
I think he meant die sizes.
Oh, die sizes. Okay.
Yes.
But it depends. It's functionality wise. Right now, on the sort of higher end processor, we do expect to the vector unit is it's not small. One typical implementation with 512-bit vectors, vector length, with the full processor, with the memory, we're targeting about 3 square millimeters and 7 nanometer technology. That would be sort of upper end of the very high end of the vector processor.
Okay, a couple more questions here. So the next one is, does baseline processor have a large L2 cache memory?
Well, all those features, as I said before, floating point, caches, local memory, all those are optional components. Size of the caches, especially L2 cache, really only is only limited by the frequency you want to operate. Typically with L2 cache sizes on a multiprocessor, we might see multi-megabyte L2 caches. So we have not had a customer run into a limit. A physical limit is if your memory is running at 500 megahertz, your processors would typically run about those frequencies. Architecture does not really impose limit.
So moving on to the next question, could you talk about the power efficiency between baseline RVP and RVV?
Yeah, so it's very hard to generalize power efficiency. So I'll give you some examples. So the baseline processor running, let's say 28 nanometer running at 1 gigahertz, doing a 32-bit integer operations, like running dry zone benchmark. We could probably get about 60 giga operations per every watt of power. That's 60 giga operations. Moving on to DSP capable processor, RVP extension, we run a different code. Obviously, the CPU is targeted for different things. For a filter, let's say you're doing a FIR filter, for that same 1 watt of power, we could do about 106, 107 giga operations. So power efficiency is twice as higher. Moving on to vectors, same 28 nanometer technology, 1 gigahertz, 512 vector length, running kernel functions like vector add, convert, and vector floating point multiply, accumulate. We could almost achieve 340 gigaflops per every watt. So the performance efficiency for the largest processor is much better, almost 5 times the small processor. However, so performance efficiency is higher as you go into more features and start executing higher level software.
Okay, the next question is, do you have a high performance out of order core as baseline?
Yeah, so our highest end core is we are introducing and we have announced the 45 series, which is superscalar in-order processor. And we are looking at introducing out-of-order processor soon, so watch out for the news.
Okay. This should be our last question today. How many layers of tensor the IP can multiply in real time, and how wide the data?
Well, the data width is configurable, both the computation width and the element width. Typically, we see about 512 to 1,000 bits, 1024 bits as sort of being a practical maximum. How many layers? Those are software, and there's really no limit to that other than the performance limits.
It looks like we got one more question about AI software inference engine. Do you have any suggestion or comparison between these two methods through NN libraries or AI compiler?
Yeah, so the using NN libraries, these are fundamental building blocks. It's highly optimized, so it gives a higher performance. However, you need to implement AI models with our NN libraries. There are third-party model converters to convert AI models with NN libraries. So there's a high performance. What you lose is flexibility that AI compilers can generate. Compiled code performs a little less than using NN libraries. However, it is very flexible. The NN libraries gives about 8 to 14x the performance boost. AI compilers probably somewhere along about the 2.5 to 6 times performance boost using AI compilers. However, AI compilers give a lot more flexibility than supporting using a NN library. But both needs to be updated if new operators come out. Or especially with AI compilers, it needs to be updated if new NN operators cannot be mapped to lower RISC-V instructions.
Great. I think we've covered all the questions today. So thank you, John.
Okay, thank you. It was a pleasure presenting to you. We look forward to seeing you in the next webinar.
Yes, and today's recording and deck will be available on Andy's website. Thank you all for joining us today. We will hold more webinars in the future, so stay tuned. Thank you and see you next time. Bye.
Bye.